How about search? Binary search? I can't jump in the middle, so that's the bad news. This remains as the efficiency of the linked list, but I still didn't get the fast search. So I need something better, and I need a new algorithm. This is divide and conquer with randomization. Okay, so what's the idea of this algorithm? Do I have some example on here? Okay, I present the example first and let's see the algorithm. So the idea is pretty much that let's suppose I have the elements, I have the numbers. So this is the sorted order. Let's suppose in my list I have number 1, I have number 13, I have number 21, then I have number 40, then 55, and 76, and 100. Let's suppose this is my numbers. Now what I do is that I divide, sorry, no, this is bad example. Okay, first I divide, okay, my numbers is that, let's suppose I have all numbers from 1 to 100 in my list. And I divide my 100 numbers into square root of n segments. And let's assume that I have really sorted, so I have all the numbers here in this slot. And now, basically what I want to do, okay, how much is square root of 100? 10. So I divide it into 10 segments. If I know how to divide it to equal. Unfortunately, I don't know. I have to rely on randomness here. But if I know my first elements have the number 1 to 9, next one is okay 10 to 20, 30, 40. So it will be all segments has exactly 10 elements. I have 10 segments and all of them have 10 items in it. So and this applies not even 100. If I have 64, n equals to 64, what is square root of 64? 8. Yes. So if I divide to 64 into 8 segments, how many items in each segment? 8. Yes. So if I divide square root of n items into square root of n segments, so 100 to 10 segments or 64 to 8 segments, the result will be square root of n 8 segments or here 10 segments. So the same number repeats. And what I do then, I do the first step is here missing. So what I do first is okay. Yeah. So these are now my breakpoints, and because I can't do this equal dividing, I take the dividing random numbers. I take randomly from the list, I have 10 random numbers. So now you can see as a result, they are somewhere divided randomly there, but the segment lengths are not equal anymore. If I select here, okay, now I regret I destroy my numbers. Let's suppose this is 21, this second one is 30, then I have 45, 55, 74, 100. Okay, I need 10 of them, so there should be more. But you get the idea. They are just random numbers anywhere. Some segments are longer, some segments are shorter. So they are not equally divided, but they are anyway divided. So at first step, what I do, I want to find the maximum number. Let's suppose I want to find number 27. Where is 27? Is it in the list? I want to find this. So I first compare this 27 of these segment borders. I find out my segments. Okay, here's a 1. Are you greater? Yes. Okay, then I have 74. Are you greater? No. 55 greater? No. Okay, 100 greater? No. 21 greater? Yes. 45 greater? No. Greater than 30? No. What more? 1 greater than 1? But that's already studied. Okay, yes. So I compare with all of these selected numbers and I will find out the maximum. Okay, this 27 is wrong. I need to have maximum here 30. So let's suppose I have 37 I search. So this number, what I find out is what is the maximum number that is smaller than the one I'm looking for. And as a result, yeah. So this is the biggest that is smaller than the number. And after that, I know that the number 37, if it exists, it must be in this segment, right? Because this number was bigger than 37 and this was smaller. So it must be in between here. So finding the biggest one that is smaller than what I'm looking for, I will find the start point of the segment. The end point I don't need to find because that's quite trivial, so I just, okay. So maybe I look at the code first. So as an input I have the array and then I have the number what we are looking for. So I start with the head and then I initialize that the maximum what I'm looking for is the first one in the list. So I have to have something. And then I start to repeat. So now in this loop I will find the maximum. I make the, and notice, I'm not doing any segmentation really. My segmentation is just an abstraction there. What I'm really doing is just selecting random numbers. So this is a kind of simulation of the segmentation. Just 10 random numbers. I take the one number there. Between this, so any number in the list, so I will take whatever there, and because they are not sorted in the array, I get any number out of it, I don't know which one. They come in just random order. I will have 10 different numbers anywhere in the list. What I do is I just take the value and see, is it bigger than my previous maximum? So if it's bigger than my previous maximum and it's smaller than what I'm looking for, so remember these conditions. I find the maximum that is smaller than what I'm looking for. I'm searching the, so if I have 10 different numbers, I want to find the biggest that is still smaller than me. So if this condition takes, then I update the maximum. I also keep the index because I don't really need the maximum number, but I need to know where is it in the list. Okay, remember, we have a linked list in the array somewhere. So having array, I have access randomly there. That's a trick. I have a random access. I can take any number anywhere. And after that, I know what is the maximum. And from that point of view, when I found the maximum, in the second step here, I do simple linear search starting from this location. Okay, now I will jump back here. So what will happen is that analyzing these numbers, 10 numbers, so all of these numbers here I have analyzed, and this is in no order. I just have 10 random numbers, whatever I get, but I will find the maximum of them that is smaller than my x. And once I have a pointer to here, so it's somewhere in the dynamic list, I have this list here. And I have found out that this is the maximum number, and my number is somewhere after that. From that point of view, I do linear search following the links. So, and now the point is that what my claim is that what is the length of this linear search? Okay, the first step, I'm looking the maximum. How many steps it needs? How I find the maximum? What is the time complexity?
The square root of.
Yes, it's a square root of n, because I'm looping here square root of n times selecting random number, so this is a constant. Copying the number, taking one comparison, two comparisons, so it's a constant number, okay, 1, 1, 1, 1 for operations. Copying it, and this happens only if it's a bigger. So this happens even less than 50% of time. But anyway, in total, this is some constant number what is spent here, but this is square root of n. So in total, this takes square root of n times constant equals to order square root of n time. So that's how find the maximum. So this is my first step. So basically order square root of n. So I a little bit simplified here because it's there were several steps to be done. So it's multiplied by some constant c. And then after that, now I claim that doing linear search. So what matters is what is the size of this segment, right? And now I claim if I'm lucky with my randomization, I have equal segment lengths. And what is my segment length is square root of n. So then the linear search here also takes order square root of n times. And if I sum it up these two, the total result will be order square root of n. So basically it's 2 times c times and 1 times, so c plus 1, so it's some constant. If that length is square root of n. And I claim that now this, yes, if I'm unlucky, this segment can be really long, right? If I divide the list, if my random numbers all happen to be in the beginning, and what I'm looking is the last element. In the worst case, my segment length is really n minus x, or n minus square root of n. So I'm unlucky. But on average, sometimes it's longer, sometimes it's shorter, but on average I claim it's square root of n. Okay, I'm not going to prove it, this is should be so obvious. However, I want to give you, okay, this is it's not proof by example or proof by students, it's a convincing the students by a simple example. Okay. So what we do is that let's assume that I have 100 numbers stored in my array with this linked structure, and now I need to select 10 random numbers. I have my random, what I'm searching for, I'm not telling you, but it is in the next slide. So you know that I can't change it in the last minute or something, so it's already written there in the last slide. And it's different what is the slides on the internet. Okay, now you are the random number generators. Give me one number between 1 and 100.
74.
30?
74.
74. Okay. Yes, you.
1.
1. Okay. You. 5. Your neighbor? 10. Okay, you?
36.
36. You?
12.
12. In the window, you?
85.
85. And you?
90.
90. Wow, I have nasty students today. You?
59.
59. Do I already have 10? 1, 2, 3, 4, 5, 6, 7, 8, 9. One more. Anybody?
99.
99. Okay. I feel that this random number generator today was really looking for the worst case, or at least a little bit. Okay, what I'm looking for is the next slide, and the number is 64. Okay, let's see. First step, I take these numbers. So any order what you generate, I just one by one. Okay, this is a bigger, okay, this is a bigger, 74, bigger, 59. Yeah, so after I analyze these 10 numbers, I will find out that 59 is the biggest. that is smaller than 64, right? Okay, how many steps I need more in the linear system? 50, 59, 60, 61, 62, 63, 64. 1, 2, 3, 4, 5. 5 steps. So 10 steps in the finding the maximum of this, plus 5 steps in total, 15 steps. Even with the nasty random number generator. If you were really nasty, you just give 1, 2, 3, 4, and 900. But I was so relieved when I hear this 59. Oh yeah, I'm a winner. If this number didn't exist here, then you can see that 36 to 64. Wow, I would end it up to something like how much? 28. So quite a long. Still much less than 100, but much longer than I wanted. I wanted a square root, it means the 10. So I wanted, on average, I claim it will be 20. 10 for analyzing the 10 numbers, and then 10 steps on average, so 20. So, yeah. So the time complexity here is really square root of n. It's I said it's not a complete solution, it's a compromise. This is more than logarithm of n, but it's still much faster than n, right? So yeah, I don't know if this data structure is really used somewhere, and I just somehow like to teach it. It's so many different elements in it. It's just the randomization, and it's also the other divide and conquer. So notice this divide and conquer, like the minimum spanning tree solution. It just doesn't divide into halves. It just divide to, it's also divided into half, but only one step. So what is the half in this sense? Half is square root. So we will have square root of elements, and the content is square root of elements. So it's, and yeah, so it will end up to 10 power 0.5.
Is that closer to log n or just n?
Well, good question. So if we have here logarithm of n, if we have square root of n, and if we have n, which is closer? Very good question, and I don't want to punish you, and this is so good question I want to put it exercise task. I think you already have one this kind of question last time with the n factor or something. So let you study this, which is closer. So, and good questions don't have answer. I don't know the answer. So you don't have to look the correct answer. You have just to find out the best together, the best answer you can come out of it, which is closer. And then I'm interested to wait the result. What do you think? Because I don't know. I would tend to say that it's closer to here. But how do I conclude it? I need a proof, evidence, something, some arguments. Okay, so that's about it today. So any questions about randomized algorithms? Okay, see you tomorrow then.